Everyone, this is Godfrey Devaputra working as Associate Professor in Department of Mechanical Engineering, Maharaj Institute of Technology, Mysore. In the previous video, I had taught you the procedure of BigM in order to solve an LPP. In continuation to that, today I am going to teach you the concept of duality. What I mean by duality is that by virtue of the relationship that exists in an LPP, which if it is called as a primal, there is a twin which is available, which can also be defined, which will then be called as a primal. So therefore, in actuality, every LPP will have a dual of a problem. So that means to say, if you have a LPP which is given and if you call it as a primal, there is always going to be a problem which can be defined by using the primal, and that will be called as the dual of a problem. In several of the cases, what happens is when you have an LPP which is given, and therefore, say for example, you have more number of constraints. In order to solve it by using any of the methods, the number of iterations depending on the number of constraints will increase. So by evolving the dual of a primal, so you will be reducing the number of constraints, so therefore it will become easier to solve the problem which is now reduced in the form of number of constraints, which is called as a primal, therefore arriving at the solution for the dual of a problem. In structure, the definition of a dual problem looks something like this. If for example, if a primal of a problem is given as maximize z equals c1 x1 plus c2 x2 plus etc cn xn, subject to constraints a11 x1 a12 x2 plus etc subject less than equal to b1. Similarly, to going up to am1 x1 plus am2 x2 plus etc up to amn xn less than equal to bn, wherein the variables themselves x1 x2 x3 etc up to xn are all greater than equal to 0. Now we can, by using the system of equation that is given here, which is now called as the primal, we can arrive at another set of equation which will then be called as a dual. The dual is always derived from the system of equation that is given in the primal. So if you observe here, I have written the dual here. The maximization problem in the primal has become minimization problem here, and I am representing the function as z star. The variables have been newly be defined as y1 y2 y3 etc up to yn, which are all greater than equal to 0. Here if you can observe, the derived form of the dual here is from that which is in the form of primal here. Here c1 c2 etc up to cn, where the coefficient of the variables in the objective function have now become the RHS of the constraints here. Okay, the RHS of the constraints here have now become the coefficient of the variable in the objective function here in this case. So therefore, how it is supposed to be written is minimize z, but the maximization problem in the primal has now become minimization problem in the dual. So here I am going to start by writing, here the objective function is supposed to be written by using the constants, sorry, the RHS that is available in the primal. We are going to define them as the coefficient of variables in the objective function of the dual. So here b1 y1 plus b2 y2 plus etc up to bn yn will become the objective function. So I'll repeat once again, minimization maximization problem has become minimization here, and the objective function is written. Now how to evolve the constraints of the dual by using the primal. So here a11 x1 has been replaced by a11 y1. Okay, so moving on, this the first constants, the first set of constants we have a11 a21 etc etc etc, all of them become the coefficient of the variables in the constraint number 1 here in the dual. So therefore here a11 a y1 plus a21 y2 plus etc up to am1 y1, which you can see from here am1 is available here. Okay, the inequality has, since now the inequality here since the objective function is here in the form of minimization problem, so for all of the constraints the inequality is written as greater than equal to, okay, and it is equated to the coefficient of the variable in the objective function, that is c1 here. Now it has become the RHS here in the first constraint. Similarly, a12 y1, a1 a22 y2, a plus etc up to am2 yn, it is all greater than equal to c2, which is the second coefficient, that is coefficient of the variable x2 in the primal problem. Similarly, going on, you can arrive at the constraints by using the constraints and the system of equation that we have in the primal, and we can make a reformulate the problem, which will be called as the dual of the problem. Before we get into the solution of a few or solution or formulation of a dual of a few problems, let me highlight the differences that we basically have between primal and dual. In the primal, if the problem that is given is maximization, it will become minimization, and we represent z as z dash. The minimization problem in the primal becomes maximization problem. The coefficient of the objective function in the primal become RHS of the constraints. Nth variable, if it is unrestricted, which I am going to explain a bit later on, nth nth constraint in the dual becomes an equation. N variables, n constraints. Similarly, m constraint is an equation, mth variable is unrestricted. M constraints, if it is there in the primal, it will become m variables. No feasible solution. If the primal has no feasible solution, the dual of that particular LPP of that primal will become an unbounded solution. So I request all of you to make note of all of these differences. We will elaborate on those differences a bit later on. Okay, now here I have taken a simple problem to basically demonstrate how a dual of a primal is written. Problem number 1, if the given problem is maximization z equals 3x1 plus 4x2 minus 6x3, this is the system of equation that is given here in front of you. Here you have to note that regardless of whether we are finding the solution or not, in order to write a primal, we need to bring the given in order to write a dual, we need to bring the primal into a standard format. Standard format here in the concept of duality simply represents that if there is a maximization problem which is given, all of the inequalities must be less than equal to, and vice versa, if the minimization function is given, all of the inequalities must be greater than equal to. Okay, we do not give any regards at this point of time for the positive and negative sign of the RHS. Okay, so now we